Hello and welcome to this lecture. In this lecture, we will discuss about designing a Kubernetes cluster. Before you head into designing a cluster, you must ask the following questions. What is the purpose of this cluster? Is it for learning or development or testing purpose or for hosting production-grade applications? What is the cloud adoption at your organization? Do you prefer your platform to be managed by a cloud provider or self-hosted? What kind of workloads are you going to run on this cluster? How many applications are to be hosted on the cluster? Few or many? What kind of applications are going to be hosted on the cluster? Web applications or big data or analytics? Depending on the kind of application, the resource requirements may vary. What type of network traffic are these applications expecting? Continuous heavy traffic or burst? Well, let's try and break down some of these. If you want to deploy a cluster for learning purposes, then a solution based on Minikube or a single node cluster deployed using kubeadm on local VMs or cloud providers like GCP or AWS should do. We have deployed such a cluster in the beginner's course. To deploy a cluster for development and testing purposes, a multi-node cluster with single master and multiple worker nodes would help. Again, kubeadm is an appropriate tool, or if on managed cloud environments, then quickly provision a cluster using the Google Container Engine on GCP or AWS or AKS solution on Azure. Let's talk about production-level clusters. For hosting production-grade applications, a highly available multi-node cluster with multiple master nodes is recommended. We'll look at more details about high availability setup with multiple master nodes later in this section. Again, this can be set up with kubeadm or GCP or using kops on AWS or other supported platforms. You can have up to 5,000 nodes in the cluster, a total of 150,000 pods in the cluster, 300,000 containers in total, and up to 100 pods per node. Now, depending on the size of your cluster, the resource requirement of your node varies. Cloud service providers like GCP and AWS automatically selects the right-sized nodes for you based on the number of nodes in the cluster. This table shows the size of the instances and their resource specifications for specific number of nodes. If you're deploying on-prem nodes, then you could probably start with these numbers as base. Cloud or on-prem, we've already discussed that all of these deployment options are available in any environment. For on-prem, kubeadmin is a very useful tool. Google Container Engine makes provisioning Kubernetes clusters on GCP very easy. It comes with a one-click cluster upgrade feature that makes it very easy to maintain the cluster. Kops is a nice tool to deploy Kubernetes cluster on AWS, and the Azure Kubernetes Service or AKS helps in managing the hosted Kubernetes environment on Azure. Depending on the workloads configured, your node and disk configurations will differ. For high-performance workloads, rely on SSD-backed storage. For multiple concurrent access, consider network-based storage. For shared access to volumes across multiple pods, consider persistent storage volumes that we discussed in the storage section. Consider defining different classes of storage and allocating the right class to the right applications. The nodes forming a Kubernetes cluster can be physical or virtual. In our case, we will be deploying virtual machines on VirtualBox environments as nodes of our cluster. You may choose to deploy on physical machines or virtual machines or cloud environments like GCP, AWS, Azure, or any other platform of your choice. We will be building a cluster with 3 nodes, 1 master and 2 worker nodes. Now we know that master nodes are for hosting control plane components like the kubeAPI server, etcd server, and others, while worker nodes are for hosting workloads. However, this is not a strict requirement. The master nodes are also considered as nodes and can host workloads. As a best practice, it is recommended to dedicate master nodes for control plane components only, especially in a production environment. Deployment tools like kubeadm prevent workloads from being hosted on master nodes by adding a taint to the master node. You must use 64-bit Linux operating system for nodes. Another thing to note is that typically you have all the control plane components on the master nodes. However, in large clusters, you may choose to separate the etcd clusters from the master node to its own cluster nodes. We will discuss more about the different topologies for that in the upcoming lecture when we talk about high availability setup. Well, those are some of the considerations for designing a Kubernetes cluster. Refer to the links in the references section for more details and some interesting reads. Well, that's it for this lecture. Well, before you go, from a certification exam standpoint, there's really nothing much you need to remember from this section. You don't have to memorize the numbers that we discussed, as these are available in the documentation page. Well, we'll get into more interesting topics in the upcoming lectures in this section, where we will provision an actual cluster from scratch by ourselves. Well, that's it for this lecture. I'll see you in the next lecture. Hello and welcome to this lecture. In this lecture, we talk about the different choices available for the infrastructure hosting a Kubernetes cluster. In the previous lecture, we discussed about the various options we have in deploying a Kubernetes cluster. Let's look at it in a bit more detail here. Kubernetes can be deployed on various systems in different ways, starting with your laptops to physical or virtual servers within your organization, as well as those in the cloud. Depending on your requirements, your cloud ecosystem, and the kind of applications you wish to deploy, you may choose one of these solutions. On a laptop or a local machine, there are a number of ways to get started. First of all, on a supported Linux machine, you can get started with installing the binaries manually and setting up a local cluster. However, that is too tedious, especially if you are just getting started. So relying on a solution that automates all that will help in setting up a cluster in a matter of minutes. We will look at some of those solutions in a bit. On Windows, on the other hand, you cannot set up Kubernetes natively as there are no Windows binaries. You must rely on a virtualization software like Hyper-V or VMware Workstation or VirtualBox to create Linux VMs on which you can run Kubernetes. There are also solutions available to run Kubernetes components as Docker containers on Windows VMs. But remember, even then, the Docker images are Linux-based, and under the hoods, they run on a small Linux OS created by Hyper-V for running Linux Docker containers. So what are some of the solutions available to easily get started with Kubernetes on a local machine? Minikube deploys a single node cluster easily. It relies on one of the virtualization software like Oracle VirtualBox to create virtual machines that run the Kubernetes cluster components. We have seen this in the beginner's course. The kubeadm tool can be used to deploy a single node or a multi-node cluster real quick. But for this, you must provision the required hosts with supported configuration yourself. So the difference between the first two and kubeadm is that the first two provisions a VM with supported configuration by itself, whereas kubeadm expects the VMs provisioned already. At the same time, it allows for deploying multi-node clusters, whereas the former doesn't. Again, deploying a Kubernetes cluster locally on a laptop is usually for learning, testing, and development purposes. For production purposes, there are many ways to get started with a Kubernetes cluster, both in a private or a public cloud environment. I would categorize them as turnkey solutions or hosted or managed solutions. Turnkey solutions are where you provision the required VMs and use some kind of tools or scripts to configure Kubernetes cluster on them. At the end of the day, you are responsible for maintaining those VMs and patching them and upgrading them, etc. But cluster management and maintenance are mostly made easy using these tools and scripts. For example, deploying a Kubernetes cluster on AWS using the kops tool. Hosted solutions are more like Kubernetes as a service solution, where the cluster, along with the required VMs, are deployed by the provider and Kubernetes is configured by them by the provider. The VMs are maintained by the provider. For example, Google Container Engine lets you deploy a Kubernetes cluster in a matter of minutes, without you having to perform any configuration by yourself. Let us look at some of the turnkey solutions. OpenShift is a popular on-prem Kubernetes platform by Red Hat. For those of you who may not be familiar, OpenShift is an open-source container application platform and is built on top of Kubernetes. It provides a set of additional tools and a nice GUI to create and manage Kubernetes constructs and easily integrate with CI/CD pipelines, etc. We have an OpenShift for Beginners course in our catalog. Check it out if you are interested. Cloud Foundry Container Runtime is an open source project from Cloud Foundry that helps in deploying and managing highly available Kubernetes clusters using their open source tool called BOSH. If you wish to leverage your existing VMware environment for Kubernetes, then the VMware Cloud PKS solution is one that should be evaluated. Vagrant provides a set of useful scripts to deploy a Kubernetes cluster on different cloud service providers. All of these solutions makes it easy to deploy and manage a Kubernetes cluster privately within your organization. You must have a few virtual machines with supported configurations in place. These are a few of the many Kubernetes certified solutions. Well, there are many more, so check them out in the Kubernetes documentation page. Let us look at some of the hosted solutions. Google Container Engine is a very popular Kubernetes as a service offering on Google Cloud Platform. OpenShift Online is an offering from Red Hat where you gain access to a fully functional Kubernetes cluster online. Azure has the Azure Kubernetes Service. And finally, Amazon Elastic Container Service for Kubernetes is Amazon's hosted Kubernetes offering. Again, these are just some of the solutions. There are many more. So what is our choice? In our case, since this is for learning purposes and considering the fact that some of you may not have access to a public cloud account, and since most of you mentioned in the poll we sent out that you prefer a local setup with VirtualBox, we chose to deploy a local Kubernetes cluster from scratch on our local system by creating several virtual machines on VirtualBox. So our design now has 3 nodes, 1 master, 2 worker, to be deployed on a laptop with virtual machines provisioned on VirtualBox. Well, that's it for this lecture. Check out the reference page to read more about many more such solutions. Hello and welcome to this lecture. We now look at high availability in Kubernetes. So what happens when you lose the master node in your cluster? As long as the workers are up and containers are alive, your applications are still running. Users can access the application until things start to fail. For example, a container or pod on the worker node crashes. Now, if that pod was part of a replica set, then the replication controller on the master needs to instruct the worker to load a new pod. But the master is not available, and so are the controllers and schedulers on the master. There is no one to recreate the pod and no one to schedule it on nodes. Similarly, since the kube API server is not available, you cannot access the cluster externally through kube control tool or through API for management purposes, which is why you must consider multiple master nodes in a high availability configuration in your production environment. A high availability configuration is where you have redundancy across every component in the cluster so as to avoid a single point of failure. The master nodes, the worker nodes, the control plane components, the application, of course, which we already have multiple copies in the form of replica sets and services. So our focus in this lecture is going to be on the master and control plane components. Let's take a better look at how it works. We've been looking at a 3-node cluster with 1 master and 2 worker nodes throughout this course. In this lecture, we will focus on just the master node. As we learned already, the master node hosts the control plane components, including the API, controller manager, scheduler, and etcd server. In a HA setup, with an additional master node, you have the same components running on the new master as well. So how does that work? Running multiple instances of the same components. Are they going to do the same thing twice? How do they share the work among themselves? Well, that differs based on what they do. Now, we know that the API server is responsible for receiving requests and processing them or providing information about the cluster. They work on one request at a time. So the API servers on all cluster nodes can be alive and running at the same time in an active mode. So far in this course, we know that the kube control utility talks to the API server to get things done, and we point the kube control utility to reach the master node at port 6443. That's where the API server listens, and this is configured in the kubeconfig file. Well, now with 2 masters, where do we point the kube control to? We can send the request to either one of them, but we shouldn't be sending the same request to both of them. So it is better to have a load balancer of some kind configured in the front of the master nodes that split traffic between the API servers. So we then point the kube control utility to that load balancer. You may use Nginx or HA proxy or any other load balancer for this purpose. What about the scheduler and the controller manager? These are controllers that watch the state of the cluster and take actions. For example, the controller manager consists of controllers like the replication controller that is constantly watching the state of pods and taking necessary actions, like creating a new pod when one fails, etc. If multiple instances of these run in parallel, then they might duplicate actions, resulting in more pods than actually needed. The same is true with scheduler. As such, they must not run in parallel. They run in an active standby mode. So then, who decides which among the two is active and which is passive? This is achieved through a leader election process. So how does that work? Let's look at controller manager, for instance. When a controller manager process is configured, you may specify the leader elect option, which is by default set to true. With this option, when the controller manager process starts, it tries to gain a lease or a lock on an endpoint object in Kubernetes named as kube controller manager endpoint. Whichever process first updates the endpoint with its information gains the lease and becomes the active of the two. The other becomes passive. It holds the lock for the lease duration specified using the leader elect lease duration option, which is by default set to 15 seconds. The active process then renews the lease every 10 seconds, which is the default value for the option leader elect renew deadline. Both the processes try to become the leader every 2 seconds, set by the leader elect retry period option. That way, if one process fails, maybe because the first master crashes, then the second process can acquire the lock and become the leader. The scheduler follows a similar approach and has the same command line options. Next up, etcd. We discussed about etcd earlier in this course. It's a good idea to go through that again now, just to quickly refresh your memory, as we're going to discuss some more related topics to how etcd works in this lecture. With etcd, there are two topologies that you can configure in Kubernetes. One is as it looks here, and the same architecture that we've been following throughout this course, where etcd is part of the Kubernetes master nodes. It's called as a stacked control plane nodes topology. This is easier to set up and easier to manage and requires fewer nodes. But if one node goes down, both an etcd member and the control plane instances are lost and redundancy is compromised. The other is where etcd is separated from the control plane nodes and run on its own set of servers. This is a topology with external etcd servers. Compared to the previous topology, this is less risky as a failed control plane node does not impact the etcd cluster and the data it stores. However, it is harder to set up and requires twice the number of servers for the external etcd nodes. So remember, the API server is the only component that talks to the etcd server, and if you look into the API service configuration options, we have a set of options specifying where the etcd server is. So regardless of the topology we use and wherever we configure etcd servers, whether on the same server or on a separate server, ultimately, we need to make sure that the API server is pointing to the right address of the etcd servers. Now remember, etcd is a distributed system, so the API server or any other component that wishes to talk to it can reach the etcd server at any of its instances. You can read and write data through any of the available etcd server instances. This is why we specify a list of etcd servers in the kube API server configuration. In the next lecture, we discuss more about how etcd server works in a cluster setup and the best practices around the number of recommended nodes in a cluster. So back to our design, we had originally planned for a single master node in our cluster. Now with HA, we decided to configure multiple masters. We also mentioned about a load balancer for the API server. So we will have that as well. So we now have a total of 5 nodes in our cluster. Hello and welcome to this lecture. In this lecture, we will talk about etcd in a high availability setup. So this is really a prerequisite lecture for the next lecture where we talk about configuring Kubernetes in a highly available mode. Well, one portion of that deals with configuring etcd in a HA mode. So in this lecture, we will discuss about etcd in HA mode. So in the beginning of this course, we took a quick look at etcd. We will now recap real quick and more importantly focus on the cluster configuration on etcd. So let's recap real quick and look at the number of nodes in the cluster, what Raft protocol is, etc. So what is etcd? It's a distributed reliable key value store that is simple, secure, and fast. So let's break it up. Traditionally, data was organized and stored in tables like this. For example, to store details about a number of individuals. A key value store stores information in the form of documents or pages. So each individual gets a document and all information about that individual is stored within that file. These files can be in any format or structure and changes to one file does not affect the others. In this case, the working individuals can have their files with salary fields. While you could store and retrieve simple key and values, when your data gets complex, you typically end up transacting in data formats like JSON or YAML. So that's what etcd is and how you quickly get started with it. We also said that etcd is distributed. So what does that mean? And that is what we're going to focus in this lecture. We had etcd on a single server, but it's a database and may be storing critical data. So it is possible to have your data store across multiple servers. Now you have 3 servers all running etcd and all maintaining an identical copy of the database. So if you lose one, you still have 2 copies of your data. Perfect. But how does it ensure the data on all the nodes are consistent? You can write to any instance and read your data from any instance. etcd ensures that the same consistent copy of the data is available on all instances at the same time. So how does it do that? With reads, it's easy. Since the same data is available across all nodes, you can easily read it from any nodes. But that is not the case with writes. What if 2 write requests come in on 2 different instances? Which one goes through? For example, I have writes coming in for the name set to John on one and with the name Joe on the other. Of course, we cannot have 2 different data on 2 different nodes. When I said etcd can write through any instance, I wasn't 100% right. etcd does not process the writes on each node. Instead, only one of the instances is responsible for processing the writes. Internally, the 2 nodes elect a leader among them. Of the total instances, one node becomes the leader and the other node becomes the followers. If the writes came in through the leader node, then the leader processes the write. The leader makes sure that the other nodes are sent a copy of the data. If the writes came in through any of the other follower nodes, then they forward the writes to the leader internally and then the leader processes the writes. Again, when the writes are processed, the leader ensures that copies of the write are distributed to other instances in the cluster. Thus, a write is only considered complete if the leader gets consent from the other members in the cluster. So how do they elect the leader among themselves? And how do they ensure a write is propagated across all instances? etcd implements distributed consensus using Raft protocol. Let's see how that works in a 3-node cluster. When the cluster is set up, we have 3 nodes that do not have a leader elected. Raft algorithm uses random timers for initiating requests. For example, a random timer is kicked off on the 3 managers. The first one to finish the timer sends out a request to the other nodes requesting permission to be the leader. The other managers on receiving the request responds with their vote and the node assumes the leader role. Now that it is elected the leader, it sends out notification at regular intervals to other masters informing them that it is continuing to assume the role of the leader. In case the other nodes do not receive a notification from the leader at some point in time, which could either be due to the leader going down or losing network connectivity, The nodes initiate a re-election process among themselves and a new leader is identified. Going back to our previous example where a write comes in, it is processed by the leader and is replicated to other nodes in the cluster. The write is considered to be complete only once it is replicated to the other instances in the cluster. We said that the etcd cluster is highly available, so even if we lose a node, it should still function. Say for example, a new write comes in, but one of the node is not responding, and hence the leader is only able to write to 2 nodes in the cluster. Is the write considered to be complete? Does it wait for the third node to be up, or does it fail? A write is considered to be complete if it can be written on the majority of the nodes in the cluster. For example, in this case of 3 nodes, the majority is 2. So if the data can be written on 2 of the nodes, then the write is considered to be complete. If the third node was to come online, then the data is copied to that as well. So what is the majority? Well, a more appropriate term to use would be quorum. Quorum is the minimum number of nodes that must be available for the cluster to function properly or make a successful write. In case of 3, we know it's 2. For any given number of nodes, quorum is the total number of nodes divided by 2 plus 1. So quorum of 3 nodes is 3 by 2, which is 1.5, plus 1 equals 2.5. If there is a 0.5, consider the whole number only. So that's 2. Similarly, quorum of 5 nodes is 3. So here is a table that shows the quorum of clusters of size 1 to 7. Quorum of 3 and 5 are what we calculated. Quorum of 1 is 1 itself, meaning if you have a single node cluster, none of these really apply. If you lose that node, everything is gone. If you look at 2 and apply the same formula, the quorum is 2 itself. 2 by 2 is 1 and 1 plus 1 is 2. So even if you have 2 instances in the cluster, the majority is still 2. If 1 fails, there is no quorum, so writes won't be processed. So having 2 instances is like having 1 instance. It doesn't offer you any real value as quorum cannot be met, which is why it is recommended to have a minimum of 3 instances in an etcd cluster. That way it offers a fault tolerance of at least 1 node. If you lose 1, you can still have quorum and the cluster will continue to function. So the first column minus the second column gives you the fault tolerance, the number of nodes that you can afford to lose while keeping the cluster alive. So we have 1 to 7 nodes here. 1 and 2 are out of consideration. So from 3 to 7, what do we consider? As you can see, 3 and 4 have the same fault tolerance of 1. 5 and 6 have the same fault tolerance of 2. When deciding on the number of master nodes, it is recommended to select an odd number as highlighted in the table, 3 or 5 or 7. Say we have a 6-node cluster. Say for example, due to a disruption in the network, it fails and causes the network to partition. We now have 4 nodes on one and 2 on the other. In this case, the group with 4 nodes have quorum and continues to operate normally. However, if the network got partitioned in a different way, resulting in nodes being distributed equally between the 2, each group now has 3 nodes only. But since we originally had 6 manager nodes, the quorum for the cluster to stay alive is 4. But if you look at the groups here, neither of these groups have 4 managers to meet the quorum, so it results in a failed cluster. So with even number of nodes, there is possibility of the cluster failing during a network segmentation. In case we had odd number of managers originally, say 7, then after the network segmentation, we have 4 on one segmented network and 3 on the other. And so our cluster still lives on the group with 4 managers as it meets the quorum of 4. No matter how the network segments, there are better chances for your cluster to stay alive in case of network segmentation with odd number of nodes. So an odd number of nodes is preferred over even number. Having 5 is preferred over 6. And having more than 5 nodes is really not necessary, as 5 gives you enough fault tolerance. To install etcd on a server, download the latest supported binary. extract it, create the required directory structure, copy over the certificate files generated for etcd. We discussed how to generate these certificates in detail in the TLS certificates section. Then configure the etcd service. What's important here is to note that the initial cluster option where we pass in the peers information. That's how each etcd service knows that it is part of a cluster and where its peers are. Once installed and configured, use the etcd_ctl utility to store and retrieve data. The etcd_ctl utility has two API versions, v2 and v3, so the commands work different in each version. Version 2 is default. However, we will use version 3, so set an environment variable etcd_ctl_API to 3, otherwise the below commands won't work. Run the etcd_ctl put command and specify the key as name and value as John. To retrieve data, run the etcd_ctl get command with the key, name, and it returns the value John. To get all keys, run the etcd_ctl get keys only command. Going back to our design, how many nodes should our cluster have? In an HA environment, as you can see, having one or two instances doesn't really make any sense, as losing one node in either case will leave you without quorum and thus render the cluster non-functional. Hence, the minimum required nodes in an HA setup is 3. We also discussed why we prefer odd number of instances over even number. Having even number of instances can leave the cluster without quorum in certain network partition scenarios. So, all the even number of nodes is out of scope, so we are left with 3, 5, and 7, or any odd number above that. 3 is a good start, but if you prefer a higher level of fault tolerance, then 5 is better, but anything beyond that is just unnecessary. So considering your environment, the fault tolerance requirements, and the cost that you can bear, you should be able to choose one number from this list. In our case, we go with 3. So how does our design look now? With HA, the minimum required number of nodes for fault tolerance is 3. Now, while it would be great to have 3 master nodes, we are limited by our capacity of our laptop. So we will just go with 2. But if you're deploying the setup in another environment and have sufficient capacity, feel free to go with 3. We also chose to go with the stacked topology where we will have the etcd servers on the master nodes itself. Well, that's it for this lecture. Thank you for listening, and I will see you in the next.
In this lecture, we will look at the kubeadmin tool, which can be used to bootstrap a Kubernetes cluster. The kubeadmin tool helps us set up a multi-node cluster using Kubernetes best practices. As we discussed, the Kubernetes cluster consists of various components, including the kube API server, etcd, the controllers, etc. We've seen some of the requirements around security and certifications to enable communication between all of the components. Installing all of these various components individually across different nodes and modifying all of the necessary configuration files to make sure all the components point to each other and setting up certificates to make it work is a tedious task. The kubeadmin tool helps us by taking care of all of these tasks. Let's go through the steps to set up a Kubernetes cluster using the kubeadmin tool at a high level. First, you need to have multiple systems or VMs provisioned. So we're going to need a couple of nodes for our Kubernetes cluster. These can be, once again, physical or virtual machines. And in the next video, in the demo, we'll actually go over how to set this up on your laptop, and you'll see that it's going to be actually very easy. Once all of the nodes are provisioned, you're going to have to designate one as the master and the rest as worker nodes. The next step after that is to install a container runtime on the hosts. So we will specifically be using containerd. And so we're going to install containerd on all of the nodes. After that, we'll have to install the kubeadmin tool on all the nodes. So the kubeadmin tool helps us bootstrap the Kubernetes solution by installing all of the necessary components on the right nodes in the right order. Following that, we have to then initialize the master server. So during this process, all of the required components are installed and configured on the master server. Then, once the master server has been initialized, but prior to joining the worker nodes to the cluster, you must ensure that the network prerequisites are met. So normal network connectivity is not enough for this. Kubernetes requires a special networking solution between the master and worker nodes called the pod network. And so once the pod network is set up, we are all set to go on having the worker nodes join the master node. And once they've joined the master node, we can then move on to deploying our application onto the Kubernetes environment. We will now see a demo of setting up a Kubernetes cluster using the kube-admin tool on our local environment. In this demo, we will see how to provision VMs for our Kubernetes cluster that will include a single master node and 2 worker nodes. And we're going to accomplish this by using 2 different pieces of software. The first one is going to be VirtualBox. So this is our hypervisor, which is ultimately responsible for running our virtual machines. And the other tool is going to be Vagrant. So this is like a automation tool that makes it really easy to spin up a whole bunch of VMs with a specific configuration. So we're going to make use of Vagrant so that all of us can kind of follow along with the exact same configuration for our VMs, and we can get those VMs up and running with just one single command. So the prerequisites, obviously, for this video is you have to install VirtualBox and you have to install Vagrant. So if you take a look at VirtualBox, you could just go to the virtualbox.org, and there's going to be a downloads page, and you could just select the specific operating system you're using, and then you could just follow the steps. Pretty simple. And then Vagrant, if you go to the Vagrant documentation, they have a walkthrough on how to install Vagrant as well. A couple of different ways to do that depending on what your operating system is. Just use whichever is most convenient for you. Now, for Vagrant, we have a Vagrant file, which is going to contain all of our configurations for our VMs. And this file has already been written out for all of you guys, and you can find that at the repository for the course. So go ahead and just clone this repository so that you can have access to the Vagrant file, and you can use that to spin up the VMs. And to clone the repository, all we have to do is go to this code dropdown right here and just copy the URL of this specific repository. Then once you do that, go to your terminal and run a git clone and then pass in the URL. And that's going to clone the repository. All right, so I cleared out the terminal, but after we clone the repository, it's going to create a folder with all of those files. And so I'm going to cd into that folder. And within here, if I just do an ls, you should see the Vagrant file right here. So let's open up the Vagrant file and let's take a look at the configuration. All right, and so in the configuration, you can see here we've set it up to have 1 master node and 2 worker nodes. The IP addresses for the host, so this has nothing to do with Kubernetes yet, the IP addresses of the actual VMs or the nodes, they're going to make use of the 192.168.56 network. And if you'd like to, you can go ahead and poke around at the rest of the configuration, but we don't need to worry too much about that. The great part about Vagrant is we can just run one command and get all of our VMs up with the same exact configuration. So I'm going to close this out. And I'm going to run a Vagrant status. And so what this is going to do is it's going to check the status of the VMs. And for the statuses for the VMs, we can see that they're all set to not created. And so you could see that we've got the 3 different VMs here, Kube Master, which is going to be our master node, and then the 2 worker nodes. And they're all in a not created state because we actually haven't brought up the VMs. So let's go ahead and do that now, and we can do that with the Vagrant up. And this is going to provision all 3 of those VMs with the exact specifications from the Vagrant file. And so what it's going to do is it's actually going to pull the Ubuntu Bionic 64 base image. And then once that image is pulled, it's able to then provision all of the different VMs. This part is going to take a decent amount of time to get all of those VMs up and running. So we're just going to have to sit there and wait. Just understand that it's not a big deal if it takes a long time. It's kind of expected. Okay, so now that it's complete, if you just take a look at the logs, you can see it actually goes step by step and provision the different VMs. So it first started provisioning the Kube Master. After it provisioned that, it then moved down to the Kube Node 1, which is the first worker node. and then it wrapped up by provisioning the cube node 02. So we've got all 3 VMs provisioned. And now if I do a vagrant status, we can take a look at the status of the VMs now that they're provisioned. And we can see that all 3 nodes are in a running state, which is exactly what we want. So now that we've got the 3 nodes in a running state, how do we connect to it? Well, we do this by running the command vagrant SSH, and then the name of the specific node we want to connect to. So if I want to connect to kube master, I'm just going to copy that. And this is automatically going to connect us to the kube master node. And so now you can see, based off of the command prompt, you can see we are now in the kube master. And if I just do an ls -la, we could see that I am in fact in the kube master. So to log out, to exit out of the session, I can just do a log out, and that's going to take me back to my local machine. And if I once again do a vagrant status, I can then do a vagrant SSH, and I'll connect to kube node 1. And connected to kube node 1, if I just run an uptime, we can see that it's been up for 3 minutes. So we are in fact connected to kube node 1. And then I'll log out of this one, and then we'll just quickly connect to kube node 2. So I'll do a vagrant SSH kube node 2. And now we're successfully connected onto kube node 2. So that's how you access all of your VMs. So we've got all of our VMs provisioned, and we're good to go. So in the next video, we're going to actually bootstrap the Kubernetes cluster using kubeadm. Okay, so we have created all of the VMs that will act as our nodes necessary to get started with creating our Kubernetes cluster. So we've got 3 nodes. We've got 1 master and 2 workers. And so just to make sure you guys understand which tab is which on my screen, you have the kube master here, and that's going to be this tab right here called kube master. And then we have kube node 1, and then we have kube node 2, which is going to be the 2 worker nodes. Now, to get started installing a Kubernetes cluster, what we're going to do is we're going to reference the documentation, and you specifically want to go to this installing kubeadm page. So this is going to walk you through the process of getting everything set up with kubeadm, and it's going to have all of the necessary links that you can refer to get all the other aspects of a cluster up and running. So this is the main page you want to start at. Just remember that. I think it's always good to remember which part of the documentation is where you want to look. And so let's quickly just go over the prerequisites. And so that's going to be under the before you begin section. So it's going to say you need to have some sort of compatible Linux host, whichever distributions are supported, and which we have successfully done in the last lecture. We deployed a couple of Ubuntu VMs, so those will meet the requirements. Here are the specs that it needs to match. So it needs to have 2 gigabytes or more of memory, and it also needs to have 2 CPUs or more. And then this is just going to go over some of the other requirements that are necessary for all of your nodes. So let's go down and let's go to this section right here where it says installing container runtime. So we're going to have to install a container runtime on all of our nodes. Which runtime you want to install is completely up to you. In this demo, we're going to install containerd. So just select this, and I'm going to actually open this up in a new tab. And so this is going to, once again, refer to a different page within the Kubernetes document, specifically the container runtimes page here. And this is just going to walk you through all of the steps necessary to get a runtime up and running. And regardless of which runtime you're using, the first thing that you're going to have to do is follow the instructions right here where it says forwarding IPv4 and letting IP tables see bridge traffic. So this is just pretty easy. All you have to do is just copy this, and we are going to run this on all of our nodes. So that's going to be both the master and the worker nodes. So I'm going to go to the master, and I'm just going to paste it here. And you should see an output similar to this. And I'll paste it here as well. And we'll do the last worker node. And after you do that, there's going to be a couple of commands that you can run to verify that everything's running. Here, we're going to verify that the BR, NetFilter, and overlay modules are successfully loaded and running. And we're going to want to do this on all 3 of the nodes. So I'll start in the master. Okay, so we see both of them are running there. And we have verified that it's running on all 3 nodes. The next thing that you want to do is verify that the following system variables are set to a 1. So we could just copy this line right here. Run it, and we can see that all of the system variables are set to 1, 1, and 1. Okay, so everything is good to go. So let's now go to the runtime that we're interested in, and we'll just select container D. So it's just going to move us down the page, and it's going to tell us the instructions that we will need to follow. So let's click on this getting started with container D. I'm going to open this up on another page. It's going to take us to a GitHub page. And there's a couple of different options of installing container D. You could use the official binaries, but I'd rather just use, apt install. So here, option 2, to install it using apt, go ahead and select your distribution. We are using Ubuntu. And that's actually going to take us to the Docker page. And so the process for installing container D is going to be very similar to installing Docker Engine. So we're just going to actually follow this page here. And I'm going to make this bigger for you guys. So let's go ahead and follow these steps. The first thing that we want to do is set up the repository. So we can just copy this and paste this once again on all 3 nodes. Okay, so we've done that. The next thing that we want to do is add the Docker official GPG keys. And we're going to run this once again, all 3 nodes. And then we'll set up the repository. And after the repository setup, let's go ahead and do a apt update. And once again, we're going to do this on all 3 nodes. And while that's running, let's take a look at the final step. And the final step is to run this command where you install all of the different packages. But remember, we're not interested in installing Docker or anything Docker related. We just want container D. So we don't actually have to copy this entire command. All we need is sudo apt install, and then we just need containerd.io. So just copy that name. And now we can run this on here. So we'll do sudo apt install, and then we want containerd.io. And I'll copy this command, and we'll run this on both of the other nodes. And after that's installed, we can do a systemctl status containerd, and we can see that it's actively running. So the installation was successful. Now, before we move on to the next step, there's actually one more thing we have to do with containerd. And if we actually scroll up on this page, and so I'm still on the container runtime page, we want to go to this C group driver section. And this section is kind of important, and I definitely recommend you guys kind of read through it just to kind of digest and understand it. But just to kind of give you a brief overview of what this section is saying, there's this thing on Linux machines called control groups. And these control groups are used to constrain resources that are allocated to different processes running on your machine. Now, both kubelet as well as the container runtime actually need to interface with these control groups to enforce various resource managements for pods. So think of things like setting the CPU and memory requests and limits. These are all things that need to be kind of communicated to the C groups. And so the kubelet and the container runtime kind of have to interact and interface with these C groups. And so to interface with these control groups, kubelet and container runtimes need to use a C group driver. And there's 2 different drivers. There's C group FS, and there's systemd. So C group FS is usually the default. Systemd is the other one. Now, which one you use is going to depend on a couple of different things, but the rule is if you are using a systemd init system, you have to use the systemd C group driver. So that means we're going to have to change it because I did mention the C group FS is the default for the container runtime. And in addition to that, whatever driver is being used by the kubelet or the container runtime, the other one has to be used as well. So if the container runtime uses systemd driver, cgroup driver, then your kubelet has to use the same exact systemd driver. You can't have one using cgroupfs and one using systemd. They have to both match. So we're going to set both of them to be systemd. So let's go ahead and do it for the container runtime. And first of all, let's verify what our init system is. And if you don't know how to do that, there's a very simple command. If you just run ps, so this is going to list out all the processes, and you grab the one with the process ID of 1, that's going to be your init system. And it's going to give you which init system. So this one's systemd. So we are in fact using systemd. And so to set the cgroup driver to systemd, if we go down to the containerd section, we're right down to here, we got containerd. Configuring the systemd cgroup driver, you have to go to the /etc containerd config.toml, and then you have to configure this. So we're going to copy this for now. And we're going to do a sudo vi /etc containerd config.toml. And this is important. Go ahead and delete all of the default configurations. You might run into some errors if you don't. Go ahead and just delete all of it. So I'm going to delete all of that. And then we're going to paste in the configuration. And I'm going to delete this line right here where it's just the 3 dots. And that's all you have to do. So we will save that. And then we'll do a sudo systemctl restart containerd. So the changes take effect. And we're going to do that for all 3 nodes. So I'll do sudo vi /etc containerd. I'm going to delete everything, and then we'll paste the config in, and then delete that line. And then we'll restart containerd. And we'll do it for the last worker node as well. All right, so the runtime is ready to go. We've got that off the checklist. Let's go back to the documentation. We want to go back to the installing kubeadm page. So this is the original page we're on. So we've got the installing container runtime done. We'll go to the next section. So the next section, we're going to install kubeadm, kubelet, and kubectl, just to kind of reiterate what all of those do. So kubeadm is actually the tool that's responsible for bootstrapping the cluster. Kubelet, that's going to be the component that runs on all of your clusters that's going to do things like starting your pods and containers. And then kubectl, that's the command line utility that we use to talk to the cluster. So let's go down here. And so this is going to contain the section that has all the instructions for installing kubeadm. And this is just going to be a cut and paste job. So I'm just going to copy this first step. And we're going to run this. And make sure to run this on all 3 nodes. We'll copy step 2. We're going to add the repository now. Okay, so we've added the repository, and then we can get all of those installed. All right, so now we've got kubectl, kubeadm, and the kubelet installed on all 3 nodes. Okay, so now we can get started on configuring or provisioning our Kubernetes cluster. So we'll go to the what's next section down here. It's going to take us to this create a cluster page, which is just going to link to the same page. So we'll go there. And this is going to go over all of the steps. Once again, you see the prerequisites. Here, you just need to make sure you have Ubuntu or CentOS or one of the distributions that's supported. And then here's all the other specs that we saw on the other page. And we want to go down to this page, this section right here where it says initializing your control plane node. The first step right here, so this command, this control plane endpoint, this is only if you're going to run with multiple master nodes. We just have one, so we can skip the first step. But for the second step, we have to first of all, you have to choose a pod network add-on. And then on top of that, when we run the kube_adm init command, which is what's actually going to create our cluster, we have to pass in this --pod-network-CIDR flag to provide what is going to be the pod network that we're going to use. So in our case, we're going to use the 10.244.0.0/16. So we'll have to pass that in. The third step right here, this is basically is telling us that kube_adm will try to automatically detect which container runtime we're using. If it can't do that, you can pass in the -s_cri socket flag and pass in the what is the specific path to your specific container runtime. But kube_adm will automatically detect that we're using container D, so we don't need to worry about that. And the last thing is when we run the kube_adm init command, we're going to also have to pass in the --API server -advertise -address flag. So this is going to basically specify what is the address that the API server is going to listen on, and we're going to set it to be the correct static IP that we set on the master node, which will ultimately make the API server accessible to all of the worker nodes on that specific IP address. So here we just pass in the IP address of our specific master node that we set. All right, and so now all we have to do is just run kube_adm init, and then we pass in those two flags. Remember, we want the --pod network flag and the --API server advertise address flag. Now, before we do that, I'm actually going to go back to the previous page. And if we go back to this cgroup driver thing that we talked about, where we have to set it to be either systemd or cgroupfs, I did mention that the kubelet also has to be set to systemd. Now, the great part is, starting in version 1.22, the cgroup driver defaults to be systemd. So that's exactly what we want, so we don't have to do anything different. However, if you're using a version before that, you're going to have to create a kube_adm config file, and you're going to have to specify this configuration right here. So kubelet configuration, and then specify the cgroup driver as systemd. And then when you run the kube_adm init command, you pass in the --config flag, and then pass in that YAML file that you configured. So we don't have to do that because we're using systemd, but I just wanted to make sure we pointed that out. So now let's go back, and we're going to run the kube_adm init command with the two flags that we want. And we're going to do this just on the master node, okay? So don't do this on all three nodes, just the master node. So we'll do kube_adm init, right? And then the first one is going to be the --pod-network-CIDR. And I'm going to set this to be 10.244.0.0/16. And then we want to specify the address of our API server. So we'll do --API server -advertise -address equals. And what's the IP address? Well, hold on. I actually have to go check that real quick. So I'm just going to comment this command out so it doesn't actually run. And we'll do an IP add. And so take a look at this interface right here. This is going to be the 192.168.56.2. So this is going to be the IP address of our API server. So let's go ahead and run that same command. And I'll set it to 192.168.56.2. And I'll delete the comment. And we'll let that run. And that's not kube_admin, it's just kube_adm. And you have to make sure that you do this with root privilege, so do a sudo. Okay, so after our control plane has successfully initialized, there's going to be a couple of things that we got to do. And make sure you don't delete what's on your screen. You actually need these steps. So the first thing is a admin.conf file was actually created so that we can actually connect to our Kubernetes cluster. So what we're going to do is we're going to create a .kube folder in our home directory, and it's going to copy this admin.conf file into that directory so we can connect to our Kubernetes cluster. And then we're going to also change some permissions so we can use it. So just take these three commands and just run this just on your master node. And so now you should be able to connect to your cluster. So if I do kubectl get pod, right? So we see no resources found in the default namespace. So that means we've successfully connected to our cluster, but it's just, we have no pods deployed. So that's perfect. Then the next step is that we have to now deploy our pod network. And so you can see all of the different network add-ons that we can use to actually set that up. So that's going to be what we're going to do next. We're going to set up the pod network. And then after that, we'll have to then go to our worker nodes and then run this command. So this is going to join the worker nodes onto our Kubernetes cluster. So definitely copy this command and make sure it doesn't get deleted because we're going to need that later. All right, so let's click on this link. It's going to take us to the add-ons page. So here we've got the different networking add-ons that we can use. In this demo, we're going to use WeaveNet. So I'm going to select the last one down here, which is WeaveNet. And so for installing WeaveNet on a cluster, all you have to do is just run this command right here. So kubectl apply, and this is going to deploy a daemon set that's going to run on our 3 nodes. So I'm going to copy this, and we're just going to run this command. So I'm going to run this just on my master node. All right, and it's going to deploy a daemon set as well as a couple of other things. So if I do a kubectl get pods dash capital A, so we can see all of the pods across all namespaces, we should see that we have one pod that's getting deployed on our control plane node. And that's what we expect. We deployed a daemon set. We're not going to see it on the worker nodes because we haven't had the worker nodes join the cluster yet. So you're only going to see just one instance of the WeaveNet pod. Now, before we move on from this section, if you actually take a look at the documentation, it's always good to read all of the documentation because there are always gotchas when we're working with all of these different technologies. Down here, under the things to watch out for page, just kind of hidden, if I zoom in for you guys, it says, if you do set the cluster cider flag option on kubeproxy, make sure it matches the IP-alloc range given to WeaveNet. So this is just basically saying that when we ran this command up here and we specified the pod, we're going to make sure that this same network is passed in using the IP-alloc range environment variable. So if I actually go down, there's going to be an example down here where it's just under the container, the Weave container, we have to specify an environment variable and then pass in the specific network that we're using. So we just have to make sure they match. So we're actually going to edit and modify the specific deployment. So if I do kubectl get daemon set, and we're going to do -a to get all of the, we're going to take a look at the WeaveNet. So I'll do a kubectl edit daemon set WeaveNet, and then -n kube-system. And we want to look for the container. And so we can see the container here, that this is the Weave container. So let's add in another environment variable. And what was it again? We'll just copy this. And we'll set the value. And this is going to be the 10.244.0.0/16. Okay, so that's all we have to do. And make sure you set it on the right container. So we want specifically the one that's the Weave container. There's a couple other containers in this daemon set. So just make sure you get the right one. And we can then exit out of this. And that's going to edit the daemon set. And if we just run kubectl get pods-a, we should see it's terminating the old one. And it's going to create a new one. So we'll give that a couple minutes to get deployed. All right, let's do a kubectl get pods-a again. And we can see we've got the new Weave pod deployed 16 seconds ago. So we're good to go. So we have set up the networking. Now the last thing that we got to do is we got to join the worker nodes to the cluster. So let's go up, back up to where that command was, this kubeadm command. And we want to just run this on our 2 worker nodes. So I'm going to copy this. We're going to run this on worker node 2. And don't forget to run this with admin privileges with sudo. And after it's completed, you should get a message saying this node has joined the cluster. So go back to the master node. We'll do a kubectl get nodes. And we can see we've got the 2 nodes. This one's still in a not ready state. So let's just run this again. And we can see now it's in a ready state. So we've now successfully joined the worker nodes to the cluster. Let's verify that everything's working. And we're going to do this by running a kubectl, and we'll just deploy some random container. So I'll say kubectl run, we'll just deploy an nginx container. So I'll say -- image equals nginx. So we've got the pod created. We'll give that a second to start up, and then we'll just do a kubectl get pod. And we can see that it is, in fact, in a running state. And we'll just go ahead and delete it now. Do a kubectl get pod now. It's deleted. So we have successfully bootstrapped our own Kubernetes cluster from scratch using the kubeadm tool. And that's going to wrap up this demo. Thank you for watching.